Welcome to the third lesson on chemistry of amines. So there is a lot in this lesson. These 3 bullet points, in particular the second one, actually cover quite a lot, all right? So it might be that there's quite a lot of instruction. There is tasks, but it might be there's quite a lot of instruction. We are going to start with a task though, with some starter questions. And I'll say the same thing that I said at the end of the previous video, which is really, you should be challenging yourself to try and remember some of this stuff. If you have to look in your notes, that's okay, but you should really try without them first, okay? So we're going to cover 3 things. We're going to cover synthesis of aliphatic amines in 2 different ways, one by a reduction reaction and one by using some year 12 recap from the halogenoalkanes topic. And we're also going to talk a little bit about reduction of nitrated arenes, which we have already covered in the aromatic topic, but we're going to talk about it again because it's a tricky equation. So then, starter questions, here we go. Pause the video, answer these as best you can, then we'll look at the solutions. Okay, so we've got some year 12 recap here from various topics. Here we go. So then we'd expect that diethylamine would have a higher boiling point than ethylamine. Think back to that first lesson. Both of these molecules can form hydrogen bonds, so that's not going to be the discriminating factor. They both have an NH bond present, which means that molecules of diethylamine will be able to form hydrogen bonds with other molecules of diethylamine, and molecules of ethylamine will be able to form hydrogen bonds with other molecules of ethylamine. That is not the issue, okay? So the issue is that we would anticipate that diethylamine would have a higher boiling point. And the reason for that is if their hydrogen bonding is largely equivalent, it's not going to be identical, but if it's largely equivalent, then size is going to be the discriminating factor. And so that's what we should arrive at. Diethylamine is a larger molecule, it's got more electrons, stronger van der Waals forces, which require more heat energy to overcome. So that links back to the first lesson. Going back a bit further, we've got a shapes question. So ammonia is a classic shape that you're anticipated to kind of be able to do, or, you know, it could be something that's very similar to ammonia. So here we are. Shape is trigonal pyramidal. In most AQA mark schemes, you can sometimes get away with tetrahedral, because even though it blatantly isn't tetrahedral, that is actually the basic shape that it is derived from. So just to be clear, anything that's got 4 pairs of electrons, the basic shape is tetrahedral, but once you look at the sort of ratio of bonding pairs to lone pairs, you might find that it's not quote unquote pure tetrahedral. And this one isn't. It's called distorted tetrahedral, or more accurately, trigonal pyramidal. Okay, and that's because it has 3 bonding pairs, but it also has 1 lone pair. The convention is to shove that on the top of the nitrogen. Okay, I've put this little balloon around it. If you haven't got that there, it doesn't need to be. It's just how I draw it when I'm teaching shapes. And what that does is the presence of the lone pair, because of the rules that are written in the answer underneath, it decreases the bond angle. You can read all that stuff. I don't need to read it out, okay? But it's to do with the valence shell electron pair repulsion theory. So that's year 12 stuff, but there's no reason why, if you were looking at amines, you couldn't be asked to answer questions like this, especially in paper 3. So then, next, we had a recap on a halogenoalkanes mechanism, which is going to be somewhat relevant for this lesson. So this is a nucleophilic substitution. Cyanide ion attacks the carbon in a halogenoalkane. You get chlorine as a leaving group, leaves as a chloride ion, and the product has changed from chloroethane to propane nitrile. The significance of adding the carbon atom that's present in the cyanide ion. I'm just reminding you of that, because remember, it extends the length of the chain, and that can be useful. It's one of the reasons that cyanide steps in an organic synthesis are often asked about, because you have to kind of spot the difference if the chain length has increased. 2 curly arrows, because it's not actually that difficult a mechanism. Further comments on that? If you didn't show the triple bond in the cyanide, most of the time you're going to get away with it, but I believe there was 1 year where it was a requirement, so you should, really. Negative charge should be located at the carbon end, but again, they're not that fussy about that. And typically your potassium cyanide or sodium cyanide is dissolved in an ethanolic mixture. So I've put eth in the kind of state symbol position. Having said that, again, that tends to matter more when doing the hydroxide example of substitution versus elimination. But again, it's a belt and braces thing. Okay, so then let's move on. So here's our first thing to look at. How do we make amines? That's what we mean by synthesis. I'm going to suggest you pause the video, read, copy, and then we'll talk a little bit about what's written down. Okay, so once you've had a chance to sort of partially digest that, here's our route to make aliphatic amines, okay? And it is called reduction of nitriles. So let's say you make a nitrile, for example, by doing a substitution with a halogenoalkane like we did in the starter. Let's say you make a nitrile. You can reduce nitriles to amines, and the combination of things that's used for that is hydrogen gas, typically in the presence of a nickel catalyst. This is the same combination of reagent and catalyst that you would use to hydrogenate alkenes, okay? Although the metal that you specify can sometimes vary. I would usually go with nickel, all right? In fact, should probably have Ni catalyst over the reaction arrow. So it's a relatively straightforward equation. You've got ethane nitrile in this case, which is being reduced to ethylamine. We have to add 4 hydrogen atoms to make that happen. And so we need 2 molecules of hydrogen. You might also see this written as 4 square brackets H. Tend to avoid it when I'm teaching this bit simply because, well, we'll talk about it a little further in the next example, but it is actually molecular hydrogen, hydrogen gas that's used in this reaction. So you don't really need the square bracketed H. You use that in the same way that you use a square bracketed O to represent some other reducing agent or some other oxidizing agent. In this case, the reducing agent is just hydrogen, so it doesn't need to be represented in that way. So then, let's get rid of that. Okay, what about aromatic amines? Well, this is recap stuff from the aromatic topic. Pause the video, digest, and then we'll talk about it a little bit. Okay, so making aromatic amines, right? This is obviously a different reaction route altogether because they're not the same thing. This was for aliphatic amines, this is for aromatic amines, okay? But because these two are the shorter parts, I'm covering them first. In this case, the reducing agent is a mixture of tin and concentrated HCl, say 6 molar, right? And in this case, we do use a square bracketed H to represent the reducing agent, okay? And the reason for that is that the reducing agent is not, hydrogen gas like it was in the previous example, all right? And you don't really need to understand exactly how this reduction works, but it is complicated. You need 6 moles of it, though, to make it work, 2 to substitute out with the oxygens on the nitro group, but another 4 for your water molecules. So then, hopefully you're happy with that. Like I said, it's recap from the aromatic topic. Let's keep going. Okay, so this is really where the kind of bulk of this lesson lies. Pause the video and just digest that for a sec. Okay, so what we're going to do is we're going to work through a series of nucleophilic substitution mechanisms, curly arrow mechanisms. Part of this will serve to recap on some year 12 content, like I keep saying, but it also is necessary really to look at the synthesis of amines. So another way that you can make amines is by the reaction of halogenoalkanes, for example, chloroethane, with ammonia. So you mix them with ammonia gas under pressure or whatever, raise the temperature a little bit as well, I suspect, and you get a nucleophilic substitution where an amine is one of the products, okay? And your halogen's kicked out as a halide ion. Now, the reason that this starts to get a bit complicated, you'll see very soon, but let's have a look at this first step. So for example, chloroethane is reacted with an excess of ammonia. We'll talk about that phrasing afterwards. So that means we have chloroethane and an ammonia molecule. I've been very nice and I've set the mechanism up for you. We need 2 curly arrows. So copy and complete. You should all be confident with this at this stage if you've been keeping up with any revision. Okay, so let's assume you've put 2 curly arrows on. If you haven't, pause the video and do it now. What we have is nucleophilic attack on the carbon atom by the lone pair on the N in the ammonia, because ammonia is the nucleophile. And we have movement of the pair of electrons that's in the carbon and chlorine bond onto the chlorine. That's what that curly arrow represents. And that's kicking our chlorine out as a chloride ion. So next, the way that this is normally taught in year 12 is that we have another 2 curly arrows for this section. Okay, so pause the video and have a go. If you're a bit less confident with this bit, I understand, but you really should know if you've been doing the recap that you're supposed to. Okay, so in this case, what we need is for the second ammonia that's present to take a hydrogen ion away from this positively charged structure, and the pair of electrons that was holding that hydrogen in place is going to move on to the N. And what that does is it puts a lone pair back onto that nitrogen. We'll see that in a minute. Quick reminder, the role of the NH3 in this step is it's considered a base, whereas in the previous step it was considered a nucleophile. And this is what makes this one of the more complicated year 12 mechanisms, right? The fact that the ammonia has this kind of dual role. So let's assume that in this reaction, everything that we did in the curly arrow mechanism has happened, and we've resulted in these products. Ethylamine is a primary amine. There's a lone pair on the N. I've only really put that there just to sort of highlight what I did in the previous step, which was moved a pair of electrons onto it. You'd also get ammonium chloride. Standard rules apply about this. If you show separate ammonium ion and chloride ion, it's totally fine. Okay, I've just put it together to keep it tidy for now. Now then, so complications. There are a couple. Okay, the first one is typically the phrasing that the AQA use in order to justify this sequence of events is they say that the halogenoalkane has been reacted with an excess of ammonia. Why does that matter? Well, there are a couple of reasons. The first one is that actually ethylamine up here, we learned in the previous lesson, we learned that ethylamine is a stronger base than ammonia because it's got a bit of that positive inductive effect, whereas ammonia has none. Why is that important? Well, the reason it's important is, if you go back here, if your ethylammonium ion already exists, as it does in this intermediate step, then it's already protonated. Along comes ammonia, which is a weaker base. Okay. Well, surely this reaction is not going to be feasible, because if the ammonia is a weaker base, how is it going to pinch a proton off the ethylammonium ion? Okay. So there's a bit of a kind of contradictory series of statements here. Let's address it, right? This is true. All the stuff that I just said is true. Ethylamine is a stronger base than ammonia. So really, this section, we shouldn't really consider it as happening. However, right, we justify it by saying if there's an excess of ammonia, you can almost think of it as being done by brute force. If there are tons of ammonia molecules around, then, you know, you're going to get a sort of a crowding out or a brute force effect where actually the ammonia molecules are able to accept a proton from the ethylammonium ions. The reason that this matters is if you actually want to make ethylamine, right, then you will need an excess of ammonia for this reason and for another reason. let's think about what happens if you have more limited ammonia. So if there's not as much ammonia available to react, you're more likely to get the ethyl ammonium ion and a chloride ion, or in other words, you're more likely to get ethyl ammonium chloride. This is an interesting and sometimes kind of irritating thing about A-level chemistry. What I would say is that if you're just learning the mechanisms by rote, you just learn that this is what happens in the year 12 halogenoalkanes substitution, nucleophilic substitution with ammonia. Okay, but like most things, there's a little bit more nuance and texture to it. Here's the other reason it matters that we specify there's an excess of ammonia. Plot twist, ethylamine is a nucleophile. We know that already because we've done some carbonyl chemistry and we've looked at the nucleophilic addition elimination mechanism, right? We know that amines can act as nucleophiles. And of course, I pointed out earlier, there's a lone pair on the N. If it's got a lone pair, it can act as a lone pair donor, could be a nucleophile. So why does this matter? And this, this is where things definitely go beyond what we will have talked about in year 12. Well, if ethylamine is formed, and if it is a nucleophile, then a reaction can occur between the excess of chloroethane and ethylamine. So let's say, for example, in this reaction mixture, okay, I didn't budget enough space for this, did I? Chloroethane is available, ammonia is available, and ethylamine is available. Well, through some random collisions, right, some of your ethylamine is definitely going to hit some of your unreacted chloroethane. And when that happens, things start to get a little more complicated. So let's have a look at it. I've been very nice and I've set up the mechanism for you. We need 2 curly arrows. There's no trick here. We need 2 curly arrows like we did in the previous example. So pause the video, copy the structures, do 2 curly arrows. Right then, so what we should have, nucleophilic attack by the lone pair on the N in ethylamine on that partially positive carbon. Chlorine's going to act as a leaving group and get kicked out as a chloride ion. We then have this scenario. So think about it as if you were going through it like you were with the ammonia. We need another 2 curly arrows, and you should all be able to do this now because I've already shown you how it works. Remember, in this case, we're assuming that the second molecule of ethylamine is going to act as a base. So 2 curly arrows, please. Pause the video. So what we should have is the ethylamine that's hanging around down the bottom pinches a proton. It's a proton acceptor. It's a base. That pair of electrons moves back onto the nitrogen, therefore taking up, getting rid of that positive charge. And our products look like this. So just let that soak in for a minute. Diethylamine, which is a secondary amine, has now been formed. And our byproduct, our salt, is ethyl ammonium chloride instead of ammonium chloride. Now, obviously that's starting to complicate things. But just back to the beginning before we push on any further, back to that phrasing. Another reason why an excess of ammonia is always specified is it's supposed to reduce the risk of what we've just seen. We call it preventing further substitutions, right? So in order to kind of stop any of the ethylamine that was formed as a product in the first step from then going back and reacting with the chloroethane, you're supposed to use an excess of ammonia and limit the amount of chloroethane, okay? Obviously, this is a bit of a random and difficult to control process, but the idea is that you try and mitigate it, you try and make it better by using an excess of ammonia. Having said that, let's assume that we don't have an excess of ammonia and this has happened. Oh no. Okay. We've got to this stage. However, there's another twist in the plot. Oh look, diethylamine has a lone pair. So diethylamine can also act as a nucleophile. I'm sure by now you can kind of see where this is going. What about that unreacted chloroethane? Well, now we've got some diethylamine that can react with it. Here's your setup. Hopefully by now you're getting the idea of how it works. All right. Pause the video, 2 curly arrows. Okay, so it's pretty, obvious, hopefully, that we have the same movements of electron pairs as we did before. There's our nucleophilic attack. There's our leaving group, carbon-chlorine bond. That pair moves onto the chlorine. Here's the next section. Let's assume that the diethylamine that's around can act as a base, and in fact it would be an even stronger base than the ethylamine or the ammonia. 2 curly arrows. Okay, so you should have paused, copied, drawn on the relevant curly arrows. Here we are. Okay, so the pattern's pretty clear. The structure's starting to get a little bit more complicated, but it's pretty clear, all right? And we end up with triethylamine, which is a tertiary amine, and this time it's diethylammonium chloride. Getting to be a bit of a mouthful. So hopefully you're starting to build a picture of the fact that actually when you react a halogenoalkane with ammonia, even if there's an excess, you're going to get a bit of a random mixture of products. It's not going to be a nice clear-cut reaction, and we'll bring that up again later. We're not quite done yet though. All right, there's a kind of end game here to get to, which involves me saying yet again that the amine that has been formed can act as a nucleophile because it has a lone pair of electrons. So I think we can go a bit quicker this time. Let's show the reaction of chloroethane and triethylamine. Pause, 2 curly arrows. On we go. Okay, don't need to discuss this time, I don't think. Now, this time, if that reaction has happened, right, then a chloride ion is kicked out. Okay, but the product is this complicated looking thing. So this thing is actually technically no longer classed as an amine. This thing is called a quaternary, so that comes after tertiary, right? Primary, secondary, tertiary, quaternary. It's called a quaternary ammonium salt. It's not an amine, and the reason it's classed technically as not an amine is to be classed as an amine, something has to have a lone pair of electrons. And there is no lone pair. So you're probably correctly assuming, if you're following the thread of this well, that the nucleophilic substitutions are going to stop now because they can't go any further. There is no lone pair on this product, therefore it cannot feed back in and react again with the chloroethane. So then, quaternary ammonium salts are what you would get if you allow this substitution to just keep going and keep going and keep going. And of course, that's entirely possible because, like I said, in this reaction mixture, it's going to be a fairly random process. There are certain things you can do to try and control it, but generally speaking, it's going to be a pain to manage, okay? The best comparison I can give here really is if you think about how halogenoalkanes are made in the first place by free radical substitution. It's a completely different mechanism. But if you think about the fact that you can get multiple substitutions in that, it's the same kind of idea, right? Which is that it's a bit of a nightmare to control. And there are ways to try and, influence the product mixture, but it's not straightforward. It's not a trivial thing. Right then. So why do we care about quaternary ammonium salts? Well, here's the reason, apart from the fact that they represent a complicated final product of all that stuff we've just discussed. They have a sort of commercial use, okay? You use them as something called a surfactant, a cationic surfactant. In plain English, this is essentially a soap or a fabric softener, something like that. You would find as part of a formulation right? A very specific mixture of things in a cleaning product, for example. So how does this kind of work? Well, let's say that we have something that's been made from methylamine reacting with a halogenoalkane 3 times. All right, so that would be how you'd make your 3 methyl groups. And then you take a much longer aliphatic chain and you attach it to the nitrogen in the same way, and you get this big, in my case, skeletal, but this big long hydrocarbon chain. Okay. So why does this matter in terms of properties? Well, let's have a little kind of color coding here. This section, the big non-polar the big non-polar section is a large hydrocarbon, and that's going to be very soluble in non-polar hydrocarbons that you find in oils and grease. Okay. This section is charged. You've got a positive and a negative ion. It's very much not non-polar, right? Because of the plus on the N and the minus on the, the halide ion. And that's going to dissolve in the sort of aqueous portion of whatever it is you're trying to clean. So the idea here is basically when you have oily kind of muck, for want of a better word, on clothes or plates or surfaces or whatever it is you want to describe, a surfactant is something that's used that has kind of character of both materials. Because if you just use something that dissolves in water, all it's going to do is it's going to move with the water. If you just use something that sticks to the grease, then all it's going to do is stick to the grease. But the idea is you get this kind of bridge between these two phases. So the non-polar section is going to move your grease along with the aqueous section. And the only way to do that really is to make a type of chemical that dissolves in both. So cationic surfactants are often quaternary ammonium salts, okay? And they have this character. And the way that you would make these is by pushing that substitution series of reactions to its limit and making a quaternary ammonium salt. Right then, let's keep going. We're nearly there. I know it feels like a lifetime ago now, but let's think about it for us, from a point of view of if we wanted to make ethylamine, the primary amine, what would we do? We could either react chloromethane, an ethanolic potassium or sodium cyanide, and then reduce it using hydrogen gas and a nickel catalyst. Remember that was something we looked at the very beginning. So we could do it that way, or we could react chloroethane and an excess of ammonia and make some ethylamine that way. So I'm not going to write anything down here. I'm just going to kind of verbally compare the two. At first glance, reaction, pathway 1, and probably at final glance as well, pathway 1 is more straightforward. The cyanide substitution is going to be relatively easy to do, and the reduction reaction is going to make a pure form of your primary amine. Doing it via the nucleophilic substitution with ammonia is going to be difficult because of trying to prevent all those additional substitutions. And even if you do prevent them, you probably have more physical separation that you have to do with your product mixture, okay? Because you'd have to take the ammonium chloride away and stuff like that. So it might be that pathway 1's better, right? Because there are fewer steps, you don't risk all these multiple substitutions, you're more likely to get a pure version of your primary amine. Having said that, just to flip it on its head for a second, anything that involves working with cyanides is going to be inherently dangerous because they are extremely toxic, okay? It's not as bad as when you use hydrogen cyanide, but potassium cyanide is still extremely poisonous. I'm not saying that one way is better than the other, by the way. It's simply kind of thinking. It's a thinking exercise. We would assume that pathway 1 is more straightforward and has fewer steps if you want a conclusion. Right then, here's your last bit, okay? Pause the video and have a go at this synthesis question. And then we'll have a look at the solutions, and then we will finally tie up this lesson, and I'll charge my iPad. Okay, so it might be that you really struggle to get going on this, and if you do, don't feel too bad, right? If you've done the bulk of this lesson and you've got to this stage, then well done you, because there's a lot going on. But if you want to get better at organic chemistry, you should really, really be trying at this stuff, especially when it's a, you know, consolidated question like this. So for the first one, we'd start with the electrophilic addition of hydrogen chloride to chloroethane, to ethene to make chloroethane. Mechanism would look like that. I've not written an equation for this one, I don't think, but it'd be C2H4 plus HCl gives you, oh no, it's there at the top. I just thought it was going to be at the bottom. There it is at the top. So then you would then react your chloroethane with ethanolic potassium cyanide, and you make propane nitrile. Mechanism is shown below. That's nucleophilic substitution. And then you would reduce it, right? I've been a bit naughty here, so I need to improve my answer, okay? First thing is, I should really have, as I said earlier in the video, 2 moles of hydrogen gas, and we should have a nickel catalyst over the top of the reaction arrow. That's how you get your propylamine. For the second question, which was a challenge question, if you tried to do this with propene, then because of the relative stabilities of carbocations, then your major products would be a secondary halogenoalkane, 2-chloropropane. Your 2-chloropropane would then make this nitrile, which is branched, methyl propane nitrile. And that would make a branched amine, 2-methyl propylamine, rather than just propylamine. Right then, I think that's definitely enough for one lesson.